This time I didn't forget to start the recording. And all right, we were dealing with...
Professor,
yeah? Tell me.
can you, if you may, you can re-explain the part when you talked about the equivalence vertex and the components?
Oh, sure.
Thank you.
So let me also take back that other page. Also, this will be useful. Okay. Okay, so let's go anyway back to the definition, because I gave also a different type, an alternative component. Okay, so first of all, very important, we are in a graph. Two vertices U and V are said to be connected if there is a UV path in G, meaning a path which has origin in U and terminus in V. And connection, you can also have a zero length path, meaning U and stop is by itself a sequence which can be considered a path, and so it is a path from U to itself. You don't need to have a loop to say for saying that U is connected to itself. Equivalence relations, let me state that. Okay. Equivalence. Relation. One, it must be reflective. Let's give a name to this relation. Let's say relation R. Okay? Reflective means that relation R on a set X. For all elements in capital X, X is in relation with itself. So our connectivity relation is in this situation. X for us in this moment is the set of vertices of our graph, and the relation is there is a path from the first to the second element. Symmetrical. For all X and Y belonging to capital X, X is in relation with Y if and only if Y is in relation with X. And third, transitive. For all X, Y, Z belonging to capital X, X is in relation with Y and this is the sign for and, y is in the relation with z implies that x is in relation with z. We'll see by solving an exercise that we have transitivity. Oh, symmetry for our particular relation. If you have a path going from x to y, the same path reversed is a path from y to x. We don't have a direction on our edges, okay? We are still far away from the chapter on directed graphs where direction is considered. Here it is a totally symmetrical relation, meaning that if vertex x is adjacent to vertex y is adjacent to vertex x, okay? And so you can actually reverse a path. If you have a path from x to y, you can take the reversed path just by reversing the whole sequence, vertex, edge, and so on, and you get a path from y to x. And then we'll see that if we have a path from x to y and the path from y to z, then we also have a path from x to z, okay? An important thing about equivalence relations is what we call the quotient set, which is the set of equivalence classes. Assume that we have an equivalence relation R on an X. Then for each small x in capital X, we can define the class of X with respect to R defined as the set of y belonging to X such that X is in relation with Y. Okay? Remark. If Y belongs to the class of X, then also X belongs to the class of Y because of the symmetry condition. So the class of X equals the class of Y. Okay. An important thing about these classes, proposition, the set of equivalence classes is a partition of X. What is a partition? A partition of a set X is a set of subsets X1, XH of X such that 1. if xi is different from xj, then xi intersection xj is the empty set. 2, if I make the union of I from 1 to h of xi, this union is the whole set X. Okay, so if I have an equivalence relation, and this is extremely general, if I have any equivalence relation on any non-empty set, then the set of equivalence classes I've defined in the page before is a partition of the initial set X. Okay, so this is exactly what we have in our situation, because we have seen that, well, not yet for the third property, transitivity, but I assure you, I promise that we'll see also that third part, but we are in presence of an equivalence relation. So if I take the equivalence classes of this relation, these are called the components of G. Okay, but this means that you must be very well acquainted with equivalence relations, with partitions, and another way of looking at exactly the same thing is what I said here, that let's use it as a proposition. The definition we already have. So let's assume it as a proposition. A component of a graph G turns out to be a maximal connected subgraph of G. And this adjective maximal is very important. In our case, it means it is a connected subgraph of G, and no connected subgraph of G contains it, being different from it. So contains it properly, we say, a proper supergraph, meaning a subgraph which contains the subgraph we are talking about without being equal to it. Okay, so my discussion was this. This was the graph, sorry, I should repeat it maybe in a new page, okay? So, uh, like this, if I remember well. Okay, this was our initial graph G. Okay, it's not 3 graphs, it is a graph, but it has different, several components. So now let's see, can we find some, sorry, I did it wrong here. Can we find some connected subgraphs? Sure, we can, for instance, take this red subgraph, okay, given by these 3 vertices and these 2 edges. Is it connected? Yes, it is. Why? Because I look at the definition. I take this vertex. Is it connected to itself? Yes, by the 0 length path. This and this vertex, are they connected? Yes, because there is this path. Vertex, edge, vertex, edge, vertex. Okay? These 2 vertices, are they connected? Yes, because vertex, edge, vertex is itself, by itself, a path connecting the 2. So this red one is a connected subgraph of our graph G. Is it a component? No, if we believe our proposition, which I'm not proving, okay? Just please believe me. Why is it not a component? Because there is a bigger subgraph, meaning a subgraph which contains this red subgraph, which is also. If I take this, and this vertex, this edge, and this edge, we also have a subgraph of G. We also have a connected subgraph of G. Why? Because also if I take this and this vertex, are they connected? Sure, by this path. This and this vertex, yes, by this path. This and this vertex, yes, by this length 1 path. So this is connected as well and contains the red subgraph properly. Is there a connected subgraph of G containing properly this green subgraph of 4 vertices? No. So this is, the green one, is this green on the right, is a maximal connected subgraph of G. So it is a component. Same argument for this part. If I take these 2 vertices and these 2 edges, this is a connected subgraph of G. Why? Because if I take any 2 vertices, there is a path, a short one, okay, connecting the 2, okay? So it is a connected subgraph. But is there a connected subgraph of G which contains properly this red subgraph? Yeah, there is this one given by this vertex, these 2 edges, but also this vertex and these 2 edges. So this red one is a connected subgraph, but is not a component. This green one is a connected subgraph. No connected subgraph of G contains it properly, and so this also is a component. And even this subgraph, given by just this vertex and no edges, is a component by itself. Okay, why? Is it a connected subgraph? Trivially, yes, okay. Is there a connected subgraph of G which contains it? No. So it is a maximal connected subgraph of G, and it is a component itself. Is now this idea clearer? The fellow, the student who asked before for an explanation is satisfied now? I would like to know what I should add to this.
Professor. Much clearer. Thank you.
Much clearer? Oh, thanks. But don't be afraid, please don't be afraid to ask again the same questions, maybe from now on this subject, maybe through the mail, and if needed, we can also have a contact by Teams, person to person, no problem, okay?
Thank you so much, Professor.
So, I said that we were dealing with some.
Excuse me, sir. Would you please show page 3 of your notes again? Just for a second.
Sure. Which one?
Page 3.
Okay. This is a very general theorem, okay?
Got it. Thank you so much.
You can have this. What can I give as a? Well, in numbers, it's very easy to find equivalence relations.
I
For
understand. I
pardon
just
me?
needed to notes. I understand it. I just
Okay, okay.
Thank you so much.
All right.
Sorry.
Very good. So I go on now. Okay. Anyway, as usual, I'll leave all these pages in the web page of the program. Okay. Just give me 24 hours. All right. So here we are. I think. Did we have any? Oh yeah, these. This is important. Oh, this is easy. Okay, let's do this. Pardon me?
I solved that one. It was really
Okay.
easy. I sent it to you.
Yes. Do you want to share your screen and show us the solution, or describe the solution to us?
I'm not sure if I can share my screen, but I can give you how I did it. I also sent the picture to your email.
I'm sorry. I have not seen my email for some hours. So now I don't know whether I can get my mail. Oh, okay. Let's do like this. If you allow me, I'll put your solution and possibly with comments if it happens not to be right in the files of the. Oh, everybody can do that. You can upload your files, your solutions, your comments to the files section of the team. Okay, and I'll do it for if you allow me for your solution. Do you allow me to do that?
Of course, sir.
Okay, so now anyway, I give my solution. Okay, so what we have to prove is small delta less than or equal to twice epsilon divided by me less than or equal to claim small delta less than or equal to 2 epsilon divided by me less than or equal to capital delta. So my solution is this. Take this. Let's visit each vertex. Our vertices assume that they are indexed like this. V1, V2, up to V knee. Okay? So now I do this. Degree of V1 plus degree of V2 plus degree of V knee. Okay? What can I say about all this?
To ask a question.
Hmm?
The delta is the maximum degree for a vertex, right?
Capital delta is the maximum in the maximal degree in the graph. Small delta is the minimum degree in the graph.
Yes,
Okay?
exactly. Okay.
Okay. So now I can do this. What can I say about the degree of V1? Surely it is greater or equal to small delta and less than or equal to capital delta. No problem about that. But this is the same thing I can say about the degree of V2 and up to the degree of V me. So now what happens? If I do the sums of these, so this, okay, and this, how many do I have of these? I have, on the left-hand side, I have ni times small delta. So this is surely ni times small delta. And here you have ni times capital delta. And you still have the inequality with sum for I from 1 to ni of the degrees of the I. But the sum for I equal to 1 up to ni of all the degrees is exactly twice epsilon. This was a theorem. Theorems are there to be used, okay? They are Kant thought. And so, as with vegetables in a can, you can open the can and serve your vegetables, and here you can serve your theorem. And so, what I have is this: ni small delta less than or equal to epsilon less than or equal ni capital delta. And so I can divide by ni, and I exactly get what I wanted. Okay? So this was rather direct as a proof. Now, show that in any group of two or more people, there are always two with exactly the same number of friends inside the group. I said that this could be reduced to the pigeonhole principle, meaning if I have that I do a, a map from a set of n objects to a set of m objects where m is less than n, then it is not possible to do injective map, where injective means different elements in the domain have different transforms in the codomain. Okay, now here, what do we use as, so first I translate into graph theoretical terms. Take a simple graph, okay, then there are always at least two vertices with the same degree. This is the graph theoretical translation. Now, look, our graph is simple, okay? And I can take as a domain the vertex set of the graph, okay? And as codomain, I take the possible degrees that you have a priori, meaning if you don't know anything about the graph itself, okay? So what happens? You have two or more people, okay. What are the possible degrees? There is a little trick to be done before, and it is this. If you have a 0 degree vertex, take it away, okay? Meaning if you have a lonely person in that group who has no friends, please take it away and just discuss all the ones which have at least one friend, okay? Be careful. All of these people have no friends, okay, but we are talking about two or more people, and so it means that all of these people have 0 degree, and so you have at least two people with the same degree, 0, okay? But if there are at least two people with at least one friend, then take away the ones who have no friends, meaning take away what are called the isolated vertices, vertices of degree 0. So now we restrict our attention with the degree 0, I am already done. Let's restrict our attention to a graph where no vertex of degree 0 appears. Okay, now what are the possible degrees? Assume that n is the number of vertices. Okay, but the graph is simple. If the graph is not simple, we can have multiple edges, and so there is no bound to the degree, because we might have that between two vertices there are 1 million edges, and so the degree is 1 million. But the graph is assumed to be simple, okay? And so what happens is that the possible degrees, if you have n vertices, none of which of degree 0, the possible degrees are 1, 2, up to n minus 1. So the set of possible degrees has n minus 1 elements. The set of vertices has n elements. And now what happens is that you are defining a map from the set of vertices, n vertices, to the set of possible degrees, n minus 1 degrees. And what happens is that necessarily this map cannot be injective, which means that there is at least a pair of vertices with the same degree. Okay? So it is mostly a set theoretical proof, which is very nice because I insist every time, several times, this is a course on mathematical methods. Okay? And set theoretical methods are mathematical methods. Any problem about this exercise?
If you allow me, I can explain in other words.
Tell me. Yeah, sure.
Thank you so much. We can consider friendship symmetric, so we can have n people starting from 1, 2, 3 up to n people, and one can have 0 friends to n minus 1 friends, like
Okay.
0, 1, 2 up to n minus 1. And let's consider that if someone has 0 friends, then no one has n minus 1 friends, and vice versa. If there is a person who has n minus 1 friends, so you cannot have a person with 0 friends. And according to
Very good.
general principle, there are two people who has the same number of friends.
Yes, always, because the number of numbers which you have in the codomain is smaller than the number of vertices that you have in the domain. Wonderful. Very good.
I don't think I think they're the same. They have the same components because one starts from one the number
It's
of
what I
people.
say. It's another way of putting the same reasoning, but it's still based on the fact that if you have a domain with n elements and the codomain with n minus 1 elements, it's not possible to make an injective application from the domain to the codomain.
I understand, but my objection is that the second domain has also n components because it starts from 0. One
Yes,
can have 0.
but you have, you got rid of it by
But yeah,
because you took the first, you took two branches. Okay, there is a person with the 0 friends, and so nobody can have n minus 1 friends, and so you are reducing anyway the set of possible of possible numbers of friends.
oh, yeah,
So your in this branch of your reasoning, the codomain is given by 0 up to n minus 2. So you still have n minus 1 possible elements.
yeah,
So,
exactly.
okay? And in the other branch, nobody has 0 friends. 0 is excluded, and you have from 1 to n minus 1, again, a codomain of just n minus 1 possible elements. So, necessarily, no injective map is possible. Okay? Thank you.
Perfect.
I think your way of expressing the thing was clearer than mine. All right.
That's all right.
So,
I can type it for the students if you allow me.
pardon me?
I can type it for the students to copy if you allow me.
Sure, please. You can do it in the chat, or later you can upload a short note as a document in the files part.
Of course,
Okay?
I'll put it in the chat in a few minutes.
As you want. Okay, let's go now to 155. If G has vertices V1, V2, Vn, the sequence D of V1, dV2, dVn is called a degree sequence of G. Show that a sequence D1, D2, Den of non-negative integers is a degree sequence of some graph, not necessarily a simple graph, in general, not a simple graph, if and only if the sum of di for I from 1 to n is even. Okay? And my hint was, if you are given such a sequence, build a graph which has this degree sequence. Okay? Has anybody done this or anyway solved the problem in any way? Priority to the outside friends. And then in the classroom, I have just one student now. I hope it's not a COVID problem, but just something else if we have just him, but I give priority to the ones who are outside. So, did anybody solve this problem? I don't ask, did anybody face this problem, attach this problem, because all of you have tried at least 5 minutes. All of you. If you didn't get a result, it's not that important. But remember, now either I or one of the students will give the answer. It's not enough to understand the answer or to repeat the answer. It is important to try to get an answer, to fail if necessary, and then you really understand the answer. But the important thing is to try, not to solve. So all of you have tried. Did anybody solve the problem? Okay, so you here in the classroom?
I think that we don't have a limit on vertices, and we can consider the 1.1 corollary on the number of odd degree vertices, which must be even. And so
No, that is not enough because you are reversing an implication. No, it's not enough to say if I have a graph, then the sum of all degrees is twice the number of edges, and so it is even. This tells you if you have a degree sequence, then surely the sum of all numbers is even. But what I'm asking is if I'm given such a sequence with the sum which is even, is there a graph with exactly those degrees?
In theory, yes, because we
Okay, I give you this sequence. Three, 6, 5, 2, 2. Let's say 7, 1.
Okay, I understand now, because we need to have the same number of vertices, like we have a degree.
You have a degree, you have a sequence of numbers, and the condition is satisfied. Okay, the sum is even. Why? Because I have 6, 2, 2, and then I have 3 plus 5, which is even, 7 plus 1, which is even. So the sum is even. Now, what is a graph having these?
But it is not possible because 7 is too much, because we need to have.
Not a simple graph. I have insisted quite a lot on this. This is true if the graph is a graph, generally not simple. Is the problem clearer now for everybody? I'm very happy that the friend here in the classroom raised the problem. Okay, the problem is if I give you such a sequence, can you draw a graph which has this sequence as degree sequence, but not only this sequence? Don't be satisfied of solving for this sequence. You must give me a procedure which accepts any sequence of numbers whose sum is even, of non-negative numbers whose sum is even, and produce a graph with that degree sequence. So I'll solve it next time, but I do want you to try 5 minutes to solve this problem. Absolutely. I hope that now the problem is clearer. Now we can reason with what you are saying on the following problem. A sequence D1, D2, Dn is graphic, is said to be graphic if there is a simple graph with degree sequence D. Show that these sequences are not graphic. I'm pretty sure that you solved it. Okay, wait a minute. Did anybody from outside solve this problem? Well, just a moment, please. Did anybody from outside solve this problem? Did anybody face this problem, try to solve this problem? 5 minutes, is that such a long? Let's do 3 minutes. You take your watch and think 3 minutes long on each of the problems I propose, okay? I'm not interested in your solving the problems. I'm interested in your trying the problems. Okay, no, don't tell me. Also, this will be for next time, sorry. Don't think you are smart if you wait till somebody solves, I solve, somebody in class or outside the class solves, and you write down the solution. This is not smart. It's extremely stupid. Okay, so we went to paths and connection. Oh, now this, I will solve this, but I hope that you have also tried to solve it. Show that if there is a UV walk in G, then there is also a UV path in G. And this was given with an example, where was it? I thought I copied it. Ah, no, here. It is here. All right. My thing was, my example was this, but this is an example, and I want you to formalize a general way of doing this. I have this walk in this graph. U, E1, and I don't even give a name here, but this vertex, E2, this vertex, E3, this vertex, E4, this vertex is E5, this vertex, E6, this vertex, finally E7, and I reach V, which is this vertex. And so this is a walk, but it is not a path. Why? Because I repeated this vertex inside my sequence. Okay, so it's very easy to.
Professor, I have a solution.
Okay, let me finish this.
Okay.
It's very easy to get the path out of this. I get rid of all this part, okay? And so I just do U, E1, E5, E6, E7, and I reach V without repeating. Now, give me your general solution.
Okay. Since we have a sequence of degrees, right? The sequence is composed of 7 degrees. Is that right?
No, wait a minute. I'm talking about this problem. That
Ah,
other problem, okay. Let's go back to that problem. All right.
I'm sorry to interrupt you.
Okay, but I guess that it's also what you were thinking, okay? But I would give priority to the outside ones. So, go
Okay.
on.
So the sequence of degrees is 7, right? There is seven sequences, right? So we have uh, uh, I'm sorry. So we have each degree are composed of a number in this sequence. Is that right?
Sorry?
With these 7 sequences, we have 6 vertices.
Uh, I don't understand. We have 7 vertices. 1, 2, 3, 4, 5, 6, 7 vertices. Okay?
Yes, exactly.
And
And
they say that the proposal is that the first one has
yes,
to be 7.
exactly. I'm sorry. So with 7 vertices, every vertex, if we need a simple graph, every vertex need to do only 6 edges. That's mean
At most,
at
6
most that
edges.
yes.
So has
So the
degree at most 6. And so
yes.
this is impossible. Quite
So
well. Quite well. You are right. This is the simplest solution for this part. Now let's go to this part where you don't have 7 anymore.
yes. Mm, For the second part, I'm sorry, I didn't have the solution, but the first I counted with the 7, so
Yes,
it was a
yes.
sign that is not a
Yes,
simple graph.
that's correct. But this is in 2 parts because in the first part you spot this 7, which is impossible in a simple graph with 7 vertices. But the interesting part is this. Did anybody solve this part where a 7 does not appear, so you cannot use the same argument?
I think with the 2 6s in the sequence.
And what does that imply?
That means there is 2 vertices that they are going to do multiple loops.
No
Oh,
loops.
no, not loops, multiple edges. Excuse me.
No, there are no multiple edges. You might have 2 vertices with 6. If you take the complete graph with 7 vertices, each vertex has degree 6. So 2, 6 is not forbidden, but it implies something.
I'm sorry, I'm missing that.
Okay, but you tried. I'm very happy of this, and you had the correct answer for the first part. I'm very happy with this. Thank you very much. Now you'll understand extremely well the solution. Which do you have a solution here?
Because the last vertex has only one, and must be two for the two six.
Yeah, exactly. Okay, I repeat what the fellow here in the classroom says. If these two vertices have degree 6, which is possible, as I said, it means that these two vertices are joined to every other vertex in the graph. And so it's impossible that there is a vertex with just degree 1, because this vertex, as any other vertex, should be joined to both these vertices. So these 6 are allowed, okay? What is not allowed having 2 6 is that we have a 1, okay? Why? Because if you have 2 6, this means these two vertices are joined to every other vertex in the graph. So every other vertex in the graph has at least degree 2. And so it's impossible with this 2 6 to have a 1. Okay? Very well for you. I'm very happy. Together, a student from outside and a student from inside solved this problem. Very good. And so now you have to do with this. And I suggest for the 5th time, don't think of simple graph. This is not valid for a simple graph. As you can see exactly here, these are sequences which respect the condition of even sum, but which do not respect the possibility of being degree sequences for a simple graph. So don't think of simple graphs, okay? And try to solve this in general. All right. Thank you. Thank you very much. Let's go, please, back to this. And so I repeat, it's clear that I have to get rid of this sort of ear that we have in our walk. But how can I formalize all this? Any proposal from outside? Yeah?
With formalizing, Professor, I think every vertex which is
No. Wait, repeat, please. I missed some words.
I was talking about formalizing the solution.
Okay.
I think we need to find a way with the formalizing that every vertex which is repeated must be eliminated from the walk in order to have a path.
Okay. This is the way to do it. And so let's think together of the thing. Don't forget, our graph is finite. Okay. And so I have a walk, and I have repetitions. If I do not have repetitions, there is no problem. It is a path, and so I have nothing to do. So let's assume that it has repetitions, okay? Can they be infinitely many? Not at all. Why? Because the walk is finite, the graph is finite, okay? So let's think we have k repetitions, meaning k pairs of vertices which appear in the walk. All right? Okay. So I have that in my walk, I find a certain vertex V1 and again V1 later on. Okay, then and maybe in between I have V2 and again V2 somewhere else. and then a certain V3 and the V3, okay, and maybe again V1 and V1. So what can I do?
May I suggest something, Professor?
No, your voice didn't come properly. I'm sorry. Can you repeat slowly?
May I suggest a solution
Go on.
for the repeat of the vertex? So once we find the repeated vertex, we begin our extraction. We take the first vertex, then the edges, then the vertex, then the edges, until that we find the repetition, which that
Okay.
means
And what do we do with this subsequence?
we take it off from the work in order to
Exactly.
find.
Exactly. You take it off. Now you have at least one repetition less. Okay.
Okay.
At the beginning, you cannot have infinitely many repetitions. You have k repetitions. Maybe k is 1000 repetitions. But now with what you have done, at most you have 999. Okay?
Okay.
And maybe less, because maybe in the subsequence you have deleted, there was already one piece of a repetition, okay, or a whole repetition. So at most you have k minus 1 repetitions. And so you can do it again, again. Each time you are decreasing the non-negative number of repetitions, okay? And so, at the end, you necessarily get rid of all repetitions. The key of this is how many repetitions do I have? A finite number, call it k. With your procedure, you get at most k minus 1 repetition in the next walk. And again, you get at most k minus 2 repetitions, and
So
so
we
on.
do factorial, right?
No, no, not. It's not a factorial. It's much less than factorial, and we are lucky with that. At most we have k such pieces of the steps of the procedure. But the important thing is that you start with a finite number of repetition, and with your procedure, deleting whatever is between a vertex and its other occurrence, you surely get one repetition less, until you have no repetitions at all. Very good. All right. And by the way, with this, we are proving an important thing, which is this, the transitive property the triangular inequality of distance for, no, it's not here. Oh, no, I had to. Okay. Metric space, a pair xd, where x is a non-empty set, and we have a function d from x cross x, meaning the set of ordered pairs of elements of x to the reals, so that for all x, y, z in capital X, 1, the number associated to the pair xy is greater than or equal to 0, and 0 is reserved for the pair of an element with itself only. 2, symmetry, d of xy equals d of yx. 3, d of xz is less than the sum of d of xy plus d of yz. There is quite an incredible number of strange distances that you have in many situations. Of course, you have Euclidean distance, but if you are walking in Bologna or in your town, surely, you are not using the Euclidean distance for going from one place to another, okay? Unless you are able to fly, okay? Do you agree with me? So what you can have is what is called the block distance or Manhattan distance, which just gives you the smallest path in town going in the street, so not going across buildings, all right? And so you have that generally the block distance is greater than the Euclidean distance. Still, it is possible to prove that it is a distance, and you can have quite a lot of theorems concerning Euclidean distance, which are also holding for the block distance for an infinite set of distances that you might have. And what the textbook says is that we can have a distance in a graph, in a connected graph. So if you, or you can extend it for, if you assume that a distance can also be infinite, okay? If vertices u and v are connected in G, the distance between u and v in G denoted like this is the length of a shortest UV path in G. If there is no path connecting u and v, we define this distance to be infinite, okay? So it is a little modification of the distance, of the definition of distance I gave you just now, okay? Show that it is actually a distance by showing the triangular inequality, that is, distance of u from u to w is less than or equal to the sum of the distance from u to v plus the distance from v to w. How can we prove this? We can prove it exactly by what we have done with walks and paths. Why? Because what we have in a graph, let's draw roughly a graph here like this. Okay, and I can take, say, no, let's do it bigger. Still more, something more here. Okay, let's take U. I must, oh, I'm sorry. If I want to make something reasonable, I need a bit more of that. Just a moment. Okay. Okay, so now let's see U, V, and W here. Okay, what's the distance between U and V? Oh, let me, just a moment. I must make it a bit more complicated for... Okay. Like this, so... Okay, so what's the distance between U and V? Let's see, I can find several paths from U to V. One could be this. And I hope it is a shortest one. Okay. Do I get any path which is shorter than that? I don't think so. Okay, so This distance is 4. Okay? 1, 2, 3, 4. And any other path from U to V has either the same number or a greater number of edges. All right? Now, what's the distance from V to W? Okay, let's see in green how I can do it. For instance, I could have this path. Okay, and every other path from V to W has either the same or more number or a bigger number of edges in it. Okay, so this is 3. Now what I can do is to build the composition of these two paths. I go from U to this, to this, to this, to this, and then I go on with the green one with this, this, and this. But even if the red one is a path, even if the green one is a path, what I've just described, this is not a path. Okay, because I have repetition of a vertex and even of an edge in this case. But what we have seen is that if we have a walk like this from U to W, then by the procedure our friend has described, we can get a path. And the path which necessarily has less edges than the sum of the number of edges of the first of the red plus the green one. Okay, are you with me? Because we have eliminated a part of the walk in order to get a path, and so we get that the distance of U and W, from U to W if you want, is surely shorter than that, and actually is even shorter than that, because we might even find something even less than this. Okay, surely we can have a path which has now the path from U to V has length 4, from V to W has length 3, and we have got a path of length 1, 2, 3, 4, 5. Okay, so having found a path of length 5, which is already less than the sum of 4 and 3, it is enough to say, okay, it's all right, the triangular inequality is satisfied. In this graph,
there is a distance of 4, Professor.
it's what I'm saying, my friend.
Okay, I thought you said 5.
No, please be careful at what I'm saying. Okay, so I must repeat. Okay, what I know, you must think in general terms. In this graph, we have that even we have less than these 5, but this 5 is enough for saying that that the distance is less than or equal 4 plus 3, and this is enough. In our cases, I was exactly saying, we have built this path with 1, 2, 3, 4, 5. Okay, so having 5, which is less than 4 plus 3, it is enough, and we are satisfied of this, because we know that the true distance between U and W will be less than or equal to 5. In this particular case, we see the graph and we can see what I was actually going to say, that we can even find this, which is of length 4, okay? And so it's even 4, but it's not that important. The important thing is I build a minimal path from U to V. and it has, in this case, length 4. I build the minimal path from V to W, okay? And it has length 3. If I compose the two, is that enough? No. Why? Because it's not a path in general. Because in this particular case, it is a walk. But we need to say we have a path from U to W with a certain length. But out of the previous exercise, we can say, okay, you have a walk from U to W, well, but then you can get out of it a path from U to W, which will necessarily be shorter than the walk. Are you with me?
Yes, 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 Professor.
So the important thing is I am sure that I can build a path from U to W out of the walk that we have obtained by composing the two minimal paths, which will not be a path in general, but we get a path which will be, okay, if the walk that we have is already a path, then we might have that the distance is actually the sum of the two distances. It's not difficult. Let me show you a very, very simple situation like this, which is this. Okay, and I have U here and V here and W here. And so you get just a possible path from U to V, just a possible path from V to W. And what you get is that if you compose the red path with the green path, okay, it is actually a path itself. And so you can see that since there is at least a path from U to V, which has as length the sum of the distance U to V 2 plus the sum of the distance V to W 3, then you're sure that your distance from U to W is at most that sum, okay? But you don't know that I was hidden to you that the graph actually contained also these two. And in fact, we have a still shorter, no, sorry. A still shorter, a still shorter path from U to, this is not W, let's call it in another way. T, okay. So you get this, okay? Wait a minute, okay, and then I give you the control. What I mean is, in this case, the juxtaposition, the combination of these two paths gives a path. We don't need to get rid of anything, but we get a path from U to V, which has length 2 plus 3, which is the sum of the distances. This is enough for saying the distance between U and W is less than or equal to the sum of the two. Maybe there is even a shorter one. Okay, it doesn't matter. We are proving less than or equal to that sum. Who's asking for control? Oh, you want to share the screen? Who does want? Is that true? You want to share the screen?
Not me, but my name is listed, but I didn't ask for any permission.
Okay, Zied?
Yes, yes, I am, but I didn't ask for permission.
Yeah, okay.
I'm sorry.
Begum? Lorenzo?
Professor, no, I didn't ask for it.
Okay, Lorenzo, Andrea?
No, Prof.
Andrea, Lorenzo? Okay.
No.
So I don't know. Okay, but please, if you want to show something directly, I hope it is possible, and we'll manage to get that. But I think that the safest way is to upload something to the file section of the team, or to write something in the chat. Okay, so I hope this is done. So this is actually a distance, okay? Oh, all right, all right. I think that we are left only, I think, with that terrible one. Where is it? This. Find a bipartite graph that is not isomorphic to a subgraph of any KQ. Has anybody tried outside?
I tried to think about it, but I didn't find a solution.
It is very difficult.
Professor,
Yeah?
I also tried and I think found one solution.
Oh, good. Can you try to... all right, let's do like that. Send it to me or upload it to the files, okay? And next time I'll discuss your solution, and if it's not valid, I'll give mine, okay? In these cases, there might be a better one or a different one than the one I have in mind, okay? And so I'm very happy if I find anyone. You here in the classroom, you think?
I think that if we have infinite vertices,
No infinite vertices.
no, because we are considering.
Okay. Good, that's nice, but in our course, all graphs are finite. Okay. That's engineering. Let's do, even if in a wild way, okay, filling a round hole with a square pipe. This is engineering. Okay, but I don't accept it. Well, all right, all right. So please upload or send me by email your tentative solutions, all right? Okay. So I'm happy with this. Try, try, try. After all, if you don't lose your mind and your sleep, these are rather nice as exercises. If you like crosswords or such things, this is better, I think. And there is a solution, and well, not everybody loves this, but it's possible to love this. Okay, I hope you enjoy. All right. Oh, no. Now there is these two. And these two require that I talk about the induction method. And this is so delicate that I'll do it after 10 minutes break. So 1743 at 1753, let's say 54, let's say 55, okay, 1755, I start again, okay? Oh, now here I pause.